Welcome guys. So in the previous video, we already talked about quotient ring. Okay, so let me just quickly remind what the hell is going on, right? So the quotient ring, sorry, not just quotient ring. So we talk about how to build a field, right? So if somebody give you a commutative ring with identity, then you can quotient the maximum ideal. So maximum ideal. So this guy become a field. Okay, so this is the construction of field. So so basically we say that how to get a ring, sorry, how to get a field by quotient and maximum ideal. Okay, so today let's talk about the field of quotient. So the field of quotient of integral domain. Okay, so in this video, so from now I decided to write mathematical equation clearly. Okay, so the integral, let me just quickly remind the integral domain means that if you get a b 0, you must have a 0 or b 0. Okay, so in the integral domain, is by default is commutative with unit. Okay, so our goal is to start from an integral domain and to construct a field. Okay, so let's maybe see an example. Should be easier. Okay, so let's take the common integral domain like integer. Okay, and how about we define another set called Q, defined to be A divided by B, such that B is non-zero. Okay, so everybody and the AB belongs to C, right? So by default, you know that Q is a rational field. It's a rational number, so it's a rational field. Okay, so it tells you that you can start from an integer to get rational field. Just define A divided by B, where B is non-zero. Okay, but this is actually a general construction. Okay, so so now we start from D, which is an integral domain, and then we can define another set. Let's say this is called the field of quotient. Let me see what is the notations. What's the good notation? Okay, so then let's see. Okay, so let's define M. Let's say this is called M, which is A divides B. Okay. So I use divides just for common notation, and B is non-zero. AB belongs to M. So another notation which is most set theoretic is I defined just using a tuple. Okay. So this is D. Okay, and so I want to give a rules. So I want to give a rules such that given a set of rules such that M becomes a field. Okay, so let me just first define an equivalent class. So M is defined to be let's say I use the tuples and B is non-zero and AB belongs to D. Okay, so I define AB the same as CD if AD equals to BC. Okay, so this is the same as you think it like this way. Okay. Okay, let's define addition. So let me just define addition. So since it's a ring, right? It's a ring, so I need to give it two operations. So for addition, I can define AB plus CD, just define to be BD, AD plus BC. Okay, how about the product? I define A divided by B times C divided by B, become AC divided by BD. Right, so this is a very stupid, very common, just as your elementary school. Okay, so theorem, M is a field. Okay. So let's see the proof. Okay, so in let's first quickly say that why this is the equivalence relation. Okay, so let's change the color. So let me just quickly prove this is the equivalent relation. So so let's see. So first we need to prove it's AB is the same as we need to prove AB is the same as AB. But this is trivial, right? Because I can choose right, if I choose AB, so if AB is the same as AB by definition, right? Because AB is the same as AB. Okay, and the AB is if AB belongs to CD, that means AD is the same as BC, right? If CD belongs to EF, that means CF belongs to DE. Okay, so I want to, so you can check that where you can prove that AB is the same as EF. Okay, why? Let's see. Let's see, because if I times B here, right, I get BC, and this I get BCF equals to BED, right? But I know BC is the same as AD, so I get ADF is DEB, which I can cancel D, right? So I got AF is BE. Okay, so this shows, so we have identity and the transition. Okay, so I finally need to prove that if A the same, if AB the same as CD, and the CD will the same will equivalent to AB, and this is by definition. Okay, so this is the equivalent relation. Okay, so let's so in order to prove its field, we need to first show. Actually, we need to first show that addition and the product is well defined. Okay, so let me just so addition is a very cumbersome, so this is just for exercise. If you guys are interested, you can check. I only want to prove the products. Okay. So let's see. I take two products A, B, and C, D. Right, and by definition, my answer will be B, D, A, C. Okay, so I use division as a notation. Okay, so I need to show that if I get A prime, B prime, which A prime, B prime is the same as AB, and the C prime, D prime is equivalent to CD, and I want to show that their product will be. So this is its product. So I need to show that I hope to show that A prime, C prime, B prime, D prime is the equivalence to AC and the BD. Okay. Right, so this is our assumption, and then we need to prove it. Yeah, so how to do this? So we need to check whether A prime, C prime, BD will be the same as AC, B prime, D prime. Okay, from here we get the A prime B is B prime A, and then we get the D prime C is the same as C prime D. Okay. So in order to prove it, it's very easy. I guess we just times these two times these two and then times these two. So we get A prime B, C prime D. So this A prime C prime BD is this side, and then let's say AC B prime D prime is AC B prime D prime. Okay, so proof is done. Okay, so the addition is very cumbersome, right? But you can check by yourself. Okay, so finally we need to check that the M has inverse or non-zero. Okay, so obviously that A divided by B is non-zero. So if A is if it's non-zero, that means A is non-zero, right? So obviously that what is the inverse of A divided by B? So the inverse should be B divided by A. Okay. AB, AB, and AB, AB. So AB, AB are equivalent to 1, 1, because AB equals to AB. So this is 1 divided by 1, which is 1. Okay. So M is a field. Okay, so this is much more powerful construction. Basically, it's called a rational field. So if somebody gives you a D, then you can construct another field. I think there's a notation use this small parentheses to say that this is a field. So Z, the fractional. Oh, okay, so I should say fractional field. So the fractional Z is just a rational number. Okay. Okay, or basically called another name is called the field of quotient. So field of quotient. Okay. Let's see. Okay, so finally, let's see. So m, right? This m is basically the fractional d. So obviously that m is larger than d. Okay, so basically we can construct a map from d to m. Okay, so this is very easy, just sending any element a into a divided by 1, or basically you use a1. Okay, so this is the embedding, right? This is the embedding because there are lots of, each d will correspond to each m, and they are all different. So this is called embed. Okay, so it means that m is larger than d as a set. Cardinality is not true, but as the set that d can be embedded in m. Right, so stupid examples that z can be injected into Q by just sending any integer to n divided by 1, which is a still integer. Okay, and the unit element, right? The unit element 1 always map to 1. Okay, I think that's it. So it's very simple. See you guys next videos.